All right, so today we have a very exciting problem. This problem is very famous. It's called the 0-1 knapsack problem. So this is a very famous dynamic programming problem. We'll see why this is dynamic programming. Basically, what is the question? The question is, write a program that selects a subset of items you're given that is maximal in value but stays within a weight constraint we're given. Here I have an example. Our weight constraint is, at max, we can pick 5 pounds worth of items. And we're given item that's 5 pounds worth $60, an item that's 3 pounds worth $50, an item that's 2 pounds worth $70, and an item that's 1 pound worth $30. So these are the items we're given. We're told, pick whatever subset of these items that is less than 5 pounds, but maximum in dollar value. We want the maximum dollars. How do we do this? This is such a tough problem. Like, how are we going to arrange our subsets? How do we solve each subproblem? Does this even subproblem down? First off, let's see why it's 0-1 first. So 0-1 means we cannot split items. We can't split items, meaning if this were not 0-1, we would be able to choose the largest item, the second largest. We would first sort it, which would cost us n log n in time. We'd pick the largest, second largest, third largest, until we run out of weight. When we run out of weight, we split the last item so that we stay within the weight constraint and still get those largest items. This is a greedy solution. This is how you would solve it greedily, but we cannot split items. This is 0-1 knapsack problem, meaning we can't split items, so we need to think a little more. So then second, when we're told subsets, we can always do complete search. Complete search is always in your toolkit whenever you're solving any interview question. We could look at all of the subsets. This would cost us, I think, 2 to the n time. Well, we'd have to investigate every subset and stay within the weight constraint, and then of all of those subsets within the weight constraint, we would take the subset with the maximum value. This is going to be exponential in time because we're taking subsets, and there's going to be 2 to the n total subsets. When we do a subset video, I'll explain why that's the case. This is exponential in time. This is a brute force solution. We can't have exponential solution. Do you see the potential to subproblem here? This is why this is dynamic programming. Let's see why and how this breaks down into smaller subproblems that we know the answer to. So why is this problem dynamic programming? Dynamic programming is, there's nothing mysterious about it. It's not about making DP tables and randomly memorizing assignments. When I was studying for programming interviews, I memorized the recurrence relation for different things like Levenshtein distance and different problems like longest common subsequence. It's not about memorizing. It's not about tables. It's about subproblems. It's about knowing the solution to a subproblem so that I can optimize the solution to my problem that I'm solving right now based on previous solutions. This is the whole point of dynamic programming. Subprobleming and remembering the answers to our previous work. Here's our example. Our maximum weight is 5. We have 4 items. We have 5 pound, 3 pound, 4 pound, 2 pound items, and you can see their values over there. Here is an example of just this is one pathway we could take during the solving of our problem, so you can see what I mean by subproblem. So we start off with 5 pounds. The total weight left is 5 pounds. Our possible choices, we can choose item 1, 2, 3, or 4. We can choose any of the items in this first step. And right now we have $0. Let's say I want to choose item 2. I want item 2. Item 2 is worth $50. Item 2 is worth $50 and it's 3 pounds. I started with 5 pounds. I have 2 pounds left. I subtracted 3. What can I choose now? I have 2 pounds left. What other items are within 2 pounds? We only have one item that's 2 pounds. So the only choice I can make from here is item 4. And how much value do I have? I have $50. Why? I have $50 because item 2, the item I chose, is worth $50. This is where it's a give and take. If we choose an item, we get its value, but we lose the amount of items we can choose. We get closer to that maximum weight. So that's why this is an optimization problem where we need to know the answer to our other subproblems that we solve. This is just one expression of one subproblem. Okay, so now we're gonna walk through the bottom-up approach. So I was just describing the top-down recursive approach where we subproblem it and fill out this table, but we're gonna walk through it bottom-up to see that way as well. So at each stage, Each of these cells represent a subproblem. So the top subproblem we want to solve is for a weight of 5. We're going to solve up to that subproblem, but what we're going to do is we're going to start from the bottom and work our way upwards. We're going to start at answering. If I have a maximum weight of 0, if I have a maximum weight of 1, max 2, max 3, max 4, once we get to max 5, we will know the optimal answer. The first thing we need to consider are what are our choices at each stage. What do each of these columns and rows represent? So in this first row, I only have item 1 to work with. I'm asking, when I'm in this cell, I'm asking, if I have a max weight of 3, using only item 1, what is the maximum weight I can get? If I'm in row 3, I'm saying, if I'm in this cell right here, cell 4, if I have a maximum weight of 4, using only items 1, 2, and 3, what is the maximum weight I can get? And you see how we're building up to the final solution. If I'm in the last cell here, if I have a max weight of 5, and I only can use item 1, 2, 3, and 4, what is my answer? That is our original question. That is what we are building up to. But first, before we get into even filling it out and doing our recurrence relation, we need to consider what our choices are. Our choice is, do we use the item in the row we're sitting in, or do we not use it? So if we choose to use the ith item, the ith is the rows we're in, the items we're considering. We either can take the weight of the previous row, we can just take what's right above us. Why do we do that? We take the row that's right above us because if we don't consider this item at all, it's not going to take away from the weight that we're using. If I can use item 1 or 2 and I have a max weight of 3, if I don't use item 2, then my subproblem becomes only using item 1, how can I maximize my price with weight of 3? If I don't choose item 2 is not going to hurt our weight. But if we choose item 2 is going to subtract from our weight, but is going to give us the value that it holds. So if I choose item 2 and I'm considering this subproblem, item 2 is going to subtract 3 pounds. Item 2 is going to subtract 3 pounds. 1, 2, 3. And we chose item 2, so then the next subproblem becomes, if I just had item 1, because we were only considering item 1 and 2. This might be a little confusing, but this is our recurrence relation. We have 2 choices to make. We only have 2 choices. Include this item or do not include it. So when we're going down our rows, each of these rows represent only considering item 1, considering item 1 and 2, considering item 1, 2, and 3, considering item 1, 2, 3, and 4. At each of those rows, we can choose to not consider or consider the ith item. Let me walk through this. It'll become more clear as we walk through this. Here's the mathematical recurrence relation in notes. What I was just saying is we take the maximum if we don't choose the item, it does not subtract from our weight, or we choose the item where we go up 1 row and we subtract the weight that the item takes away, but it contributes its value. The item contributes the value that it gives us. Otherwise, we just take the row above us if this item does not weigh, and if this item is over the weight constraint, and we can't even include it at all. So an example of where we would just take the value above us, where we couldn't even consider including this item, is if we were looking here, we have the subproblem. For the max weight of 2, if I can consider item 1 and 2, what is the maximum weight I can get? Well, item 2 is 3 pounds. We can't do anything with that. And it turns out item 1 is also 5 pounds. We can't solve for 2 pounds. Both of these are going to fall through, and we're not even going to choose. They'll just end up being 0. You'll see as we fill it out. So now that we've gone into sort of what's about to happen, let's actually fill out this table and go through the logic of the comparisons we're going to make to find our globally optimal solution. Alright, so we're in the first row. We're considering our first class of subproblem. So item 1, only considering item 1. What is the maximum weight what is the maximum value I can get with a weight constraint of 0? Well, I mean, it's 0. We can't choose any items, so we put 0. The answer is 0. What can we do if we're choosing a weight constraint of 1? And keep in mind, item 1, how much does item 1 weigh? Item 1 weighs 5 pounds. We can't answer anything until we get to 5. How are we going to answer it for 1? We can't. 1 is a weight constraint. We can't even choose item 1. Item 1 is the only item we have. So all of these just became 0 because subproblem. 2 max, 3 max, 4 max. If 4 is my maximum, I can't choose item 1. It's worth 5 pounds. It's never going to work. But then it says 5 pounds. If we only have item 1 and our maximum weight that we can reach is 5 pounds, well, we can choose item 1. Now we can because it's worth 5 pounds. So what is the value of item 1? The value of item 1 is $60. So we choose item 1 and we reap $60. So now we are finished. This is row 1. These are answers to subproblems. These cells are not magical. This is nothing magical. These are all answers to subproblems. We asked ourselves 6 questions here, and we got 6 answers, and in the next row, we're going to use these 6 answers to further our progression to the global optimal solution. That is the answer that we're looking for. So now, next row, item 1 and 2. We're considering item 1 and 2, and now what is the most optimal solution we can get with 0 as our max weight? We can't choose anything, it's 0. What is the optimal weight we can get if we are choosing between, we have item 1 and 2, do we pick or leave item 2 if our max weight is 1? Well, item 2's max weight is 3 pounds. So item 2 is 3 pounds. We're never going to get to choose it. So each time we're going to take from above us because we can't choose item 2. We're going to have to take from here, take from here. But why do we do that? Why did we just take from above us? Because at each stage we're making choices. The choice we made is we can't choose item 2. Item 2 subtracts nothing from our weight. We didn't choose it. So we need the answer to the subproblem, same weight. Weight doesn't change because we couldn't choose item 2. We need the answer to the subproblem above it. So this should start making a little more sense. Very difficult to grasp at first, but let's keep going through it. So now we're at 3 pounds. We can consider item 2. So we have the choice between don't choose item 2. We can get $0. Don't choose item 2. We can get $0 for a max weight of 3. Or how much does item 2 weigh? 3. 1, 2, 3. We go up 1 row. Why did we just go up 1 row? We go up 1 row because we are choosing it now. And we need to see what it would be if we could also choose item 1. So now we're in this, and then we go 0. 0 plus the weight we would reap if we took item 2, 50. So we just compared 50 versus 0. Which do we want to choose? 50. 50 maximizes what we take. So for the next row, now we're free to choose item 2. Item 2 is 3 pounds. Past here, we can choose it. So now let's go 1, 2, 3, 1. Now we add 50, 50 versus 0, 50. And now we need to see, so think about this. 1, 2, 3, we're gonna be doing like that. We're gonna be doing don't memorize the pattern, think about the subproblems. So we're comparing 60 against 1, 2, 3, go up 1. This is if we choose this, 0 plus 50 is 50. 50 versus 60. If we do choose item 2, we can get $50. If we don't choose item 2, we can get $60. Which do we choose? We don't choose it. We don't choose item 2, we keep $60. Why? Because we can get $60. We can get $60 if we just choose item 1. Why would we choose item 2? Do you see we are answering questions as we go down this table. This is not a memorizing thing where you figure out like the formulas you're going. You're thinking about this and you're seeing what the answer is to your subproblems as you go down. Alright, now that we're starting to get this, let's speed things up and start going through these a little faster. So we now can consider item 3. We can take item 3 or we can leave item 3. Item 3 is 4 pounds. So what we do is, 4 pounds, we're not going to be able to consider item 3 until our subproblem gets here. So what we're going to do is we're going to take from the top. We can't even pick item 3. So we're going to take from the top as if we didn't pick item 3 because we can't pick item 3. So now, okay, we took from the top, that makes sense, but now we can choose item 3. Item 3 is 4 pounds. So if we choose item 3, 1, 2, 3, 4, we chose item 3, it subtracted 4 pounds from the max weight, 0. 0 plus 70. If we do choose item 3, we can get $70. If we don't choose item 3, we can get $50. Which are we going to choose? We're going to choose item 3. We're going to take $70. Now let's do that again. 1, 2, 3, 4. Item 3 is 4 pounds. We can reap $70. We can reap $70, or we can take $60. Don't choose it, choose it. Don't choose it, choose it, right? $70 or $60. Which are we gonna take? We're gonna take 70. And now what do you see? We answered all the subproblems. If I consider just item 1, if I consider just item 1 and 2, if I consider just items 1, 2, and 3, we're so close to the solution. Now let's solve the last row. So this item is 2 pounds. We can't do anything here. We can't do anything there. It's 2 pounds. We're not gonna be able to choose it. We won't be able to choose it. We won't be able to choose it. Now we have an opportunity to optimize. Let's see what it is. So this item is 2 pounds and it's worth 30. So 1, 2, 30. 30 plus here is 30. So 30 versus 0. If we choose the item, we get $30. Don't choose it, get $0. So let's choose it. Okay, so now let's do the next one. 1, 2. If we choose the item, we get 0 plus 30. We get $30. If we don't choose it, we get $50. What do we choose? 50. So let's do it again. 1, 2. If we choose the item, we get 0 plus $30. We get $30 versus $70. Which do we choose? 70. Okay, so now you're starting to get it, and we're at the last step. We're at the last cell. This is the problem we want to answer. We did not answer the problem we were given. We answered all of these problems, all of these subproblems we answered. We did not answer the top. We built up to this answer and optimized along the way. Now our global solution will be optimized. So now, let's go back to 1, 2, 50. So this subproblem was answered with 50. So what we know is if we add item 4, now we can add $30 in value. So $30 in value, 80. 80 if we choose item 4. If we do not choose item 4, we can get 70. 80 versus 70, 80. So what is the answer to the question with this? The answer is 80. If we have a max weight of 5, and if we can choose items 1, 2, 3, and 4, our answer is 80. 80 is the maximum value we can get while staying within the weight constraint. And this is how dynamic programming works. And this is how the subproblems break down. So a question you might get asked is, what items did we choose? What items did you choose? How are we going to know that? So let's switch marker and let's look at this table. Let's not follow any patterns. Let's not try to trace things and follow the pattern. Let's think about what we just did. So here we had 2 choices. Choose item 4 or don't choose it. If we had chosen item 4, then that means it's going to be this cell's value, 2 over and 1 up, plus 30, which is this, right? If we had not chosen it, it would be this value. And this value is not this value. That means we did choose item 4. We did choose item 4. So yes, we chose item 4. So item 4 was chosen. So now let's go down here. Let's go back. Okay, we chose item 4, and now item 4 takes us to this subproblem. Subtract 2 pounds. Item 4 takes 2 pounds away because it weighs 2 pounds. Go up 1, and now we see 50. And now that we see 50, we say, hey, wait, is this the same value as it is above us? Yes, but look, it's worth value 70. Go over 1, 2. 70 plus this is not this. This means we chose to not choose this item. That means we just took this value, we chose to not choose it. So skip up here, because we didn't choose item 3, and now we're at this subproblem, considering max weight 3, and items 1 and 2 are choosable. So now we have 50. Did we take from above us? No. Item 2 is worth 50. Yes, we got it from here. So now item 2 was chosen. And then now item 2 was chosen, and then we're at 0. And then we're finished. So what do we see? Our optimal answer is item 2 and item 4. So this is the 0-1 knapsack problem. The thing is, how does this solution adapt for other things? How does this translate to other problems? So the key is identify the recurrence relation. When you get a problem that is something you could subproblem, tell your interviewer, I'm looking for the recurrence relation. I'm looking for how this can break down into subproblems. You can do this bottom up like this, or you can do it top down recursively. I prefer top down recursively because it seems more natural, because at each point, recursion is a beautiful way to express decisions as you go downwards and go towards your answer. Oh, and this is going to be big O of n times m time complexity and n times m space, or n times weights. So the n, the max weight times the number of items. If we call the number of items n and we call the max weight m, So it would be n times m, because as you can see, we make an n times m matrix for space, and then we would have to solve n times m subproblems. So that's why our time complexity is n times m space n times m. But we can make the space complexity better, but we'll leave that for another day. This is the 0-1 knapsack problem, and this is dynamic programming. There's no magic to it. It's very, very difficult. It's something that takes time, and at your best, just try to think as much as you can. Very difficult problems, very hard to grasp. It took me like a month to grasp this. But yeah, this is the 0-1 knapsack problem. And yeah.